about the concepts that they made when they started air traffic control with computers. He's going to be followed by Neville Evans, who wrote the software, or all the writing software. And finally, Ben Trassowen, who is involved with the work now at TMC, preserving his machine. So, John, over to you.
Thank you. Well, this afternoon is principally about the 9020 system that was installed at West Drayton, London Air Traffic Centre, which, for those of you who don't know, which I think is very few in this room, was about an RAF base 3 miles north of Heathrow. This was the main air traffic control computer from the 1970s onwards. But I want first to talk about some of the computers that came before the 1920, in order to give some background, and also because it's a very interesting story in its own right. I'll see if I can work this machine. So, I'm going to cover the Ferranti Apollo computer, which was installed at Prestwick in 1961. That was really the first one. Then followed by the Ferranti Hermes, which was installed at LATSI in 1968 and went live in 1968. And followed that by the Marconi Myriad, which went live in 1972. And then I'm going to go on to discuss that in spite of these promising British developments, we ended up with an American system. And I'll try and explain why that happened. Now, these early computers were introduced principally to print flight progress strips. So, what's a flight progress strip? I've got some examples here. Have you got a pointer, by the way? Is there a pointer? Oh, thanks. So this is one of the main tools of air traffic control and still is to this day. These are 8-inch paper strips, and they contain essential planning information for the controllers. And so we take this central one here, you can see here's a British Airways Speedbird. That's the call sign BAW13J. It's estimated at 1549 at a fix called Croft. Now these strips were put in little holders and put on a strip flight planning board. You can see here the planning boards where the strips were placed, and that meant the controllers could shuffle these things and organise the traffic in a suitable way. This is actually a picture of the planning cell at West Drayton, which had just moved from Heathrow in 1966. That was before the radar moved, radar followed. Now, writing these strips out before computers by hand was obviously a very tedious, labour-intensive business, and so it was natural to think this would be an obvious candidate for computerisation. In fact, you might think it's a very simple computer task, just a printing task, like printing invoices perhaps. However, that's not really the case. It turns out that it isn't quite as simple, because the first problem is you have to decide which strips to print. And that's not a simple problem, because it depends where the route of the flight is going through the airspace and how the airspace is sectorised. And that turns out to be not only a geographical but also a geometrical problem, because it's a three-dimensional problem. And the second problem with strip printing is that the system has to be ultra reliable. Any system in air traffic control mustn't break, because it's no good having a computer down, the traffic is still going to come at you. So that's the second problem. Now the first computer to tackle this, so I'll go back to that. The first computer was the Apollo system at Prestwick. I don't have a picture of that. And that was installed in 1961, and the strip printing problem was relatively simple, because the route structure over the Atlantic is a set of parallel tracks, with reporting every 15 degrees west. So the problem of where to print the strips was fairly straightforward. We now have to wait 7 years for the next one, which is the Hermes computer. And that was installed at West Drayton. The total system was called MiniCap, which stands for Minimum Capability. And in the picture there you see two 19-inch racks, one of which contained two computers, one of which was this support computer compiling programs against. And you can see that it's a paper-based machine. You can see the paper spewing out there at great amounts. Now the Hermes was a version of the well-known Ferranti 1600B military computer, based on a 24-bit word. Initially it came with 8K store, but this was later upgraded to 32. Functionally, MiniCap was quite sophisticated. It held a model of the airway structure and used wind data to calculate estimated times of arrival. Flight plan data was entered via electric typewriters, and strips were then output at a central position in the ops room. But MiniCap's reliability was poor. Apparently, the mean time between failure of the MiniCap system was only 72 hours. Although the Hermes mainframe computer had an MTBF of 6 months. However, MiniCap continued in service until it was replaced by the 9020 in 1975. The next development was the mediator system. This is where things begin to get interesting. Whereas MiniCap's strips, once printed, had to be amended by hand, in mediator, it was the intention the machine would continue to hold flight data in its store so that it could be updated online. So if a controller received a position report from an aircraft, he could then enter that as an amendment message, and the machine would then calculate all the ETAs down the route. That would minimise the manual updating of strips, but also increase the accuracy of the times on the strips. Now, mediator was originally conceived in the early 1960s as part of the now famous, or should I say infamous, Linesman Mediator project. I'm sure everyone's heard of that. This was an integrated civil air defence, all singing, all dancing computer and data handling system. It had to handle flight plans and radar data. But over time, the air defence part got separated out from the civil part, and the radar got separated from the flight planning parts. So that at the end of 1965, a call for tender was put out specifying the mediator element only. Here is a summary of the requirements for the mediator flight plan processing system. I've extracted this from the Ministry of Aviation specification issued in March 1965. And in fact, I have a copy of it here. You can tell that's the original because it's printed on foolscap. Now, although it's got the Ministry of Aviation name on the front, most of the content was produced by the Royal Radar Establishment because they were the design authorities. Now, just going through these requirements, it was required to handle both civil and military flights, which is a problem on its own because the method of control was different in the two areas. Flight data was required to be held in a real-time database, as I've explained. The third point was there was an option to use electronic data displays, which were just then becoming available, as well as printers. The thinking here, presumably, was that paper strips could be phased out. Now, the last point is perhaps the most interesting. The specification called for a downtime of not to exceed 30 seconds in 5 years. Well, I can tell from your reaction that that was a completely impossible requirement, but we didn't know at the time. Now, Marconi won the competition And they put forward a system based on a 3-processor system based on their new Myriad computer. So the 3 prongs, as they were called, each one ran the operational software, so they were all parallel running. And then every now and then the results were compared. Another innovation was a solution put forward for the user interface. This was based on a touch bar screen. Have I got the touch bar screen? No. I haven't. That's the Myriad computer. And I think you can see the 3 Myriads there. Captures. The touch bar screens is a picture that basically what you have here is 4 rows of wire, embedded wires, and they're annotated by software. So these were in effect the soft keys that we're now so familiar with. It's important to remember that in 1965, visual display terminals were only just coming into widespread use, and most input was based on command lines and fixed format messages. So here I would suggest that Marconi were ahead of the field. And remember that Xerox PARC only invented the graphic user interface a decade later, in 1975. Actually, I suspect that the touch bar screen was invented at Northern, but it'd be interesting if anyone here can confirm that. Now, it turned out the mediator spec was a bit too ambitious for the technology available. Marconi struggled to get the software to work, and they had to pull more and more programmers into the team, including contractors from SciComm. This slide shows a quite dramatic build-up in the software team as they tried to get the software to work. The initial estimate for the project was 15 to 25 man-years. And as you can see, that was hopelessly optimistic.
Probably 18.
18?
Probably.
that was the best guess, yeah. And you can see at the end of the project you had over 100 programmers. But there was actually a more fundamental problem with the Marconi solution. The machine just wasn't big enough. It was found that a store limited to 32K locations could not accommodate the full flight database. There was no obvious escape route from this, although I believe several solutions were tried, and perhaps people can comment on that later. Now, to be fair to Marconi, this wasn't really their fault. The storage required had increased since the original procurement action. The original spec was related only to the southern centre, whose airspace stopped to 53 degrees north. That's the line running east-west, just north of Nottingham. But now, the northern centre, which ran up to the Scottish border, was to be included, because during the time at which the system was being developed, the two centres had been amalgamated. And we now had a London air traffic control centre that controlled all the airspace up to Scotland. So the effect of this was that the number of active flight plans the system had to handle had doubled. But in retrospect, it seems that Marconi had simply bitten off more than they could chew. So what to do? Well, the decision was made to confine the Marconi system to the military operation, where there were fewer flights, and then look for another solution for the civil airspace problem. Now, at this time, 1971, there were a number of systems being developed worldwide which could have been relevant. This shows the principal ones. In France, they had already implemented strip printing at the minicab level as early as 1961 using an IBM 650. Anyone remember the IBM 650? They were currently planning a more sophisticated real-time system under the Contra program and had placed an order in 1969 to equip 3 en route centres with dual CII 770s, which were actually Sigma 7s. And the Sigma 7 was a 32-bit machine marketed by Scientific Data Systems and was a competitor of the IBM 360. In Holland, they had also implemented strip printing using a system called SATCO. This went online in 1968. They were then planning to implement a system called SARP, which included radar. I think this was based on an SMR4 signal processor, 24-bit mainframe machine, but haven't been able to confirm that. In Sweden, they were at the time just introducing a radar system based on a mini-computer, the Sensor 900, and that was marketed by Standard Radio and Telephone, which was an ITT subsidiary. And then there was Eurocontrol. Eurocontrol seems to be a bit behind the times here, and they were not planning to implement their sensor until 1974, last year. And finally, last but not least, we come to the US situation, which was much ahead of Europe at the time. We had 20 en route centres, up to 20 en route centres, I'm not sure whether they were all implemented at this time, running IBM equipment under the National Airspace System, NAS. Radar data was handled by Raytheon, although some of the larger centres had IBM on the radar side as well. So the conclusion of this review was that because the European systems were rather specialised, whereas the US system was adaptable over 20 centres, it would be much easier to implement the US system than any of the Europeans. And there was another point: the European airspaces were quite small compared with the UK. So now we come on to the advantages of the 1920. Yes, the advantages of the 1920. Firstly, it was designed to be easily adapted to any operational environment via a set of adaptation tables, and Neville will go into this hopefully in a bit more detail. This meant that the US hardware and software could be imported into the UK without modification. Only the data tables had needed to be defined. The adaptation philosophy had the advantage that changes could be easily made to keep in step with the changes in the ATC world, which in fact occurred quite regularly on a monthly cycle. Lastly, you didn't have to know anything about the software to make these data changes, so the job could be given to retired air traffic controllers who were quite happy to do this and had the experience. Right, the second advantage of the 1920 was expandable, because it was a multiprocessor system, and so you could just plug more, well, in theory you could plug more processors in. It wasn't quite as simple as that. The third advantage, and quite an important one here, from the start, the 1920 was designed to handle radar and flight plan data. Now, from the flight plan point of view, this was very important because it relieved controllers of the need to put in those position reports. The radar data kept the flight plan data up to date. In particular, the radar data automatically activated a flight when the flight took off and the flight departed. So previously, departure messages had to be put in every time there was a departure. Now the radar can pick that up and revise all the ETAs along the route. This function was known as automatic DM. From the radar processing point of view, it was also very important because it meant that flight plan data could be included in the labels which were labelling the targets on the radar screen. In particular, the call sign of the flight could be shown, making identification easy. Also, it could show a symbol showing the route of the flight, which was also a help to controllers. Another advantage, the 9020 was a tracking system. It meant that the track could be projected ahead to see if there were any conflicts in the airspace. And this was really quite an important safety feature. Fourthly, free software. I've noted here that software came free because the software licenses were owned by the US FAA, Federal Aviation Administration, and were made available free to the UK under an intergovernmental arrangement. So we only had to pay for the IBM hardware. I believe it was about £5 million in 1970 money. However, I should add, on the cost side, the 1920 required quite a large staff to maintain it, and so if you think of through-life costs, it probably was quite expensive. Lastly, the system was working. In view of these factors, I think you would agree the decision to purchase the 1920 was a no-brainer. The only problem was that the system wasn't British. So I'll come back to this point in a bit. Now, the 1920 was ordered in 1973, delivered in 1974, and to the amazement of NAT staff, installed at West Drayton inside a week and was up and running. They just couldn't believe this. Here's a picture of it. It's quite a contrast with the previous computer systems that we've looked at. And you might ask, well, was all this equipment, this IBM stuff really necessary? And I think the answer to that is that the previous systems that had been tried had failed. We just simply didn't have enough processing power. Now, Neville was going to say more about the 1920. I'll just say that it was based on IBM 360 processors with separate storage elements, punch card input, and lots of backing stored. In fact, you can probably see here, there's some tape, old IBM tape units, and here I think probably a 1403 line printer. And so it's all standard IBM here. Right, well, I'm getting slightly ahead of myself here. We must go back to the decision to buy the 1920. This was hugely controversial at the time. Many felt the system should be British, not foreign, especially since it was being paid by taxpayers' money, partly anyway. So to meet these criticisms, the government suggested a compromise solution. CAA would be allowed to purchase only the central part of the system from the US, and the peripheral parts would be supplied by UK industry. Now, it so happened that this was fairly easy to do because the system was partitioned into three main pieces. You had the central processor, which was the IBM 9020D. You had a radar processor, I shouldn't really have said a radar display processor, which was supplied by Raytheon. And then on the right, you had some update equipment, which allowed the controllers to quickly put messages into the system. Not quite sure who supplied that in the US. But as far as the UK were concerned, the plot was, okay, we buy the main system from IBM, but in order to keep British industry happy, we'll offer the radar display processor to Tesla, and we'll offer the update equipment to Marconi, keep everybody happy. Now, Plessy took up the offer, and Marconi declined. So in 1973, CAA placed an order with Plessy for a radar subsystem. At the same time that it placed an order with the FAA for the 1920D system. As for the computer update equipment, the Q, the CAA came up with their own solution using the Myriad as a message handling front end. It's quite interesting. So there you've got the touch wire terminals, and they send the selection, touch wire selection to Myriad. The Myriad makes up 9020 input messages and files them into 9020 when they update the database. Moving on to the Plessy system, which was called the PRBS, was based on, I'm not going to say much about this because the other speakers will cover this, but just to say that it was based on DEC processors, and it had a bypass mode, a standalone mode, which meant that if the 9020 went down, it was taken out of service for any reason, the radar system could keep going. And then lastly, one version of it was the RF system, which we're going to hear about later, which was used for incident analysis. And I'll just show you a quick picture of that, which I took last week when I was at Bletchley. I'm sure Ben will say more about that later on. Right, now, summary then. On the FDB side, we've got, starting in 1961, we've got the Apollo and the Hermes, which undertook the flight strip printing task. Then we come on to the Myriad and the 9020, which contains an online database. And on the RDB side, which I haven't said much about, we've got the Mod 1, I haven't said much about this, but the RDB side, especially when using the Modular 1 computer for radar data processing. But when the PRDS contract came, they came to the conclusion that Mod 1 was not reliable enough for air traffic control reasons, purposes. So they went over to DEC. Then we had a period of evaluation. And then, so step 1, 1920, went into 1925. But step 2, which was the radar, integrated with radar, didn't happen until 1981. So there's quite a long gap before we got radar. Right, I think that's just about as far as I go. But just before I start, I must show you this picture, which may bring tears to some people's eyes. Here we have some of the people who are instrumental in the 1920 decision. Left one, here's Ricky Wade.
Can you get near the microphone?
Chris will remember this. It's not a grainy picture.
Can you stand near the microphone? Can we get this out?
Okay. Well, you probably, some of you anyway, will recognise these characters. We've got Ricky Wade on the left, Dave Thompson, then we've got Gordon Hurst, who was the FAA test coordinator, Harry Cherry, who I think was DG of Tails at the time. I'm not quite sure.
Harry Cherry was an ATCO.
Sorry?
Harry Cherry was an ATCO, Chief ATCO.
Was an ATCO?
Yeah.
Okay. He appears to be taking delivery of it. Then we've got Joe Leftarty, who was the IBM site manager, Al Dixon, and finally but not least Stan Price, who played a major role in supervising the acquisition of the 9020 software. Now, while we're talking about people, I'd like to end by thanking all those who have contributed to this tour, and in particular to Dave Hewitt, who's not here today, unfortunately. I think he went on holiday. But he'd been extremely helpful in supplying information and allowing us to use material from his LATSI brochure. That's as far as I'm going. So I'd like now to ask Neville to take us through the 9020 itself.
Right, as you go down Neville Evans, I worked in the early days on 9020 software after it had been delivered to West Drayton. There were, in fact, one or two small things that we had to change fitted in with what the UK controllers wanted. Right. As John has indicated, early workers in the field of automation to support air traffic control soon found the machines of the day struggled to meet the requirements for both availability and fast response times. They also found out that designers were poor at estimating not only the code and data sizes, and therefore the memory, but the processing power as well. So when the American Federal Aviation Administration decided in the mid-1960s to build a computer system for their national airspace control system, they chose for their en route facilities a multiprocessor design based on the most powerful, or one of the most powerful series available at the time, the IBM 360 series. Now, although IBM had envisaged multiprocessors in the 360 range, they hadn't really engineered them for the availability requirements of the FAA. So, in fact, they had to modify the machines slightly in order to meet the availability requirement. And this multiprocessor was called 9020 in IBM's nomenclature. In 1968, they installed a prototype 9020A for part-time use in the Jacksonville Center in Florida. You can see it's a pretty big installation, and we've got rows of tape decks, and there are 6 processors in there, 6 IBM 360 processors in total, doing different things. And from the experience they gained with the 9020A, they developed the 9020D, which was the production system that they rolled out across the US into 20 en route centres. And as John said, it was also procured and installed at West Drayton near Heathrow, and was put into operational service in 1975. And the 9020 was engineered in what were called configurable elements, and these elements could be switched in and out in real time, which was something that was pretty advanced at the time when you compare it to the capability that commercial systems had. So, just running through these quickly, the main processing was done in a thing called the computing element. This was a 360-65. A lot of input-output was done by modified 360-50s. The storage was broken up into elements of 128K words. There were quite a few tape units for a variety of purposes, and the 9020D had disk drives as well. And I think I'm going to say a bit more about that later. There was a very special bit of kit called the peripheral adapter module, and this was specially designed, and this wasn't really based on their commercial equipment. And I'll talk a lot more about that later. So, for the UK operation system, they bought a 3 computing element system, and then obviously they call that the triplex. And for development, they bought a freestanding single 360-65 plus suitable bits to configure it into a test and a development system. Okay, here we've got a schematic of a typical 9020D configuration. This isn't the one at West Drayton, but it shows you the basic elements. So we have storage elements, we have computing elements, and here we have the input-output control elements, normally abbreviated to IOCs. Now the IOCs did all the input-output, as I mentioned, and they had 2 high-speed selector channels, so things like disks and so on would be driven through the selector channels. And there was also a multiplexer channel, and here there was something rather special, which I'll talk about later, which was a channel-to-channel adapter. And the peripheral adapter modules I mentioned earlier, with hams also connected into the IOCs. There were various other things which I won't go into at the moment, and banks of tape decks as well for various purposes. Perhaps a few more details about what these elements were. I mentioned the computing element was a 360-65. How many 360 programmers have we got in the audience? Okay. Okay, so I'll run through some of the basic details. It was a 32-bit machine with 16 working registers. It had a large instruction set with 24-bit addressing. Now, instructions that address memory could reference a base register and an index register, so there was quite a lot of flexibility in constructing addresses. The machine was basically byte orientated, but normal words were 4 bytes. In order to configure a working system out of all these bits, there were special registers called address translation registers, and these were set up by special IBM designed instructions which were additional to the standard 360 set, but there were special 9020 instructions for setting up the overall configuration. Okay, the IOCEs, I mentioned the select channels for the high-speed stuff, so you could drive basically one device to a select channel at a time. The channel-to-channel adapters were connected to the display channel that John mentioned earlier on. The reason why the selector channel is used is that there's an awful lot of data that has to pass through into the display channel, and you want it to pass through quickly. The multiplexer channel had 256 simultaneous sub-channels. So you could put all your slower speed devices onto the multiplexer channel. The tape decks, you might be interested in what the tape decks were. They were 2401s, half-inch reel-to-reel, and they wrote a 9-track tape of 800 characters per inch at 60 to 90k bytes per second. And there were 14 procured for the UK operation system. Obviously there were more on the development system as well. And let's see, the storage elements. For the UK operation system, or the initial operation system, 7 SEs were procured, which gave you 896k words, or about 3.5 megabytes. The disks, the 2314s, there was a control unit and 8 disk spindles. So each spindle had a 2316 disk pack, which had 11 disks in it, 14 inches in diameter, half an inch apart, each pack running on a single vertical shaft. So the 20 surfaces formed 203 channels and held about 30 megabytes. Now, I hope this isn't too much detail. I guess that people like you would be interested in some of this stuff. Okay, so an interesting point about the fact that you have a computing element separate from the input-output computing element is that when a compute element wanted to do an input-output instruction, it was quite a complicated sequence. It would execute a start I/O in the CE. The channel command words would then have to be supplied to the IOCE, and the channel command word would be obeyed there, and the input-output would take place into the IOCE, which would then place the resulting data in the storage element where it could be accessed from the CE. Right, I'll talk a bit more about the peripheral adapter modules later. So here we see a typical en route control sector, a suite of equipment. And John mentioned that a lot of ATC planning is done with flight strips. So we can see we've got a flight strip printer, and then the racks for organising these into time sequence at various fixes. And we've also got a plan view display, which is driven by the display channel that John mentioned. And let's see, what else we got? Oh, yes, we do have computer readout devices for text, and we have computer entry devices for update. Now, as John mentioned earlier on, initially it was thought that there wouldn't be a requirement for update from individual sectors. So the update equipment was missing in the original implementation, and updates had to be done by supervisory staff from their positions. Even before the touch ones, yeah. Yeah, I mean, that didn't last long. As was customary in those days, the machines had very elaborate front panels, and all the registers could be displayed. You could set up data on the keys. You could select whatever device that you wanted to IPL from on rotary switches here, and press the big red button, and hopefully it would IPL. Thing of the past now, mostly. Okay, PAMs. Right, this is a schematic of the PAM towards the end of the 1920s life in the late 1980s. So quite a few things have been added from the original installation. And this, in fact, is the interim sector update, which is the touch wire input that came through the Myriad that John mentioned earlier on. I think probably wasn't used much by this time, I think. There was a great deal of radar data coming in through things called common digitizer adapters. And I'll say more about radar later on. Let's see, what else do I want to say about that? Flight strip printers, yeah. So the main output in the initial installation were the flight strip printers. And I've got some flight strip material in here, so it was fanfold stuff, and it was ripped off. And then it was mounted in these things, so these would be in the racks that you saw at the sectors. And of course the great advantage of a flight strip is that when the power goes off, it's still there in front of you, and you can write on it in your red pen and so on. And if necessary, you could actually pass it on to the next sector. But of course, there were always plans to replace those electronically. Yes, John mentioned the interim sector update. Well, in the 1980s, it was replaced by a deck-based system. So that then was capability for a much better input at all the sectors. Now, what about the software? Now, as John mentioned, it's often referred to as the NAS system, and the software was originally called the NAS Stage A, not surprisingly. And the basic stuff that was supplied to the UK, obviously a real-time operating system was required. IBM called it Monitor. The flight data processing, radar data processing, an awful lot of offline stuff. Because the US Federal Aviation Administration was going to roll this out over 20 en route centres, they had a big budget to allow them to develop some really substantial offline aids. So it was possible to write very elaborate simulated input scripts for testing, and there were also a very substantial checker and compiler of the adaptation data that John mentioned, and I'll talk more about that later on. And then for offline analysis, there were also substantial tools, including the capability for doing really detailed output of table data that had been recorded by the online system. Languages. It was written in BAL and Jovial. Now, BAL was IBM's standard assembler, and it was used where efficiency was seen to be paramount. So the operating system was written in BAL, and quite a lot of the radar processing software was written in BAL because the frequent input of lots of radar data was seen as a processing challenge. So Jovial. Jovial was originally developed for the US Air Force, in fact, and it was taken up by a lot of US government departments. And some of you might notice it looks a little bit like Coral. Anybody use Coral? Okay, a few people. One of the interesting things was that you could provide status values for certain items. So instead of indicating different states by 1, 2, and 3, you could actually give them a bit more meaningful names. So here, was W1 STA an update or not? So it helped a little bit when you were programming. Data. The data was stored, universal data, which was shared by programs, was stored in tables of items. The overall name of this was a comp pool, so Coral people recognise that name, I think. And by convention, each table had a name comprising 2 alpha characters. And then you had the following characters within. So here we have the FP table, the flight plan table, or a small extract of it, in fact. And so you've got 3 extra characters for defining your items. Now, I ought to say that there were several hundred items in the full FP table, and there were also 500 odd tables in total, so it was a substantial system. Now, John mentioned the very important concept of adaptation. Now, the Americans had to roll it out to 20 centres right across the US. Now, every centre obviously has its own airspace structure. There's lots of different airports and the airways and so on, all have to be defined. And even the equipment at the site is different because some sites were larger, some sites were smaller, and so on. And anyway, the equipment would change over time. And as John mentioned, the airspace would change over time. And in fact, there's a worldwide update cycle called the AIRAC cycle, whereby changes to airways and restrictions on airways and so on are published to pilots and operators. And of course, the system has to be able to cope with this and update the data in the system. And so every system might have to update its online software every month, in fact. So I mentioned earlier on, we had this, what was it called, the Adaptation Control Environment System. So ACES was the system, offline system, that was used to check the validity of the data that you set up, and then to analyze it into table overlays that you would put into the system build, which you would have then on the operation system. So I'll talk a little bit now about how the adaptation worked. It's such an important concept. And as John said, it did enable an enormous amount of flexibility, and also, of course, it provided employment for ex-controllers. And of course, the advantage the ex-controllers were, they knew all about the airways, they knew all about the airspace structure, so they were pretty good at coding up that sort of stuff. So this is a schematic of UK airspace I think towards the end of the 70s. So you can see there's quite a lot of controlled airspace. So all commercial aircraft would be flying in these controlled airspace areas. And in those days, airways had names which were colour and a number, and maybe south or north as well. Now, today I want to talk about Amber 34, just crossing here, crossing the channel. So this is a small extract from a navigation chart. So you can see it's quite a complicated business. But just note here we've got a navigator distance measuring equipment at Midhurst. And I don't know if you could make it out, but up hour 34 was running down here. And if you could just note here also a fix, a waypoint, Echo Bravo, but it's also got a subname, PED. And here we've got the distance measuring equipment at Chartres, CHW. So how do we put this into the system? Okay. The X controllers would code up this data to go into ACES. So number 34, Midhurst, PEB, Chartres, CHW. There's a couple of extra fixes in here which are to do with the boundary crossing over into France, but we need to go into those. So you can see each of these fixes has quite a lot of data associated with it. So P is for the priority of posting strips for that fix. V introduces some numbers that define the sectors where the strip should go. There may be, well there are, airways that can join at this fix. And these are the airways that can connect there. Sorry, I should say connect rather than join. Because here we've got a list of coded lanes for airports, and this fix mid is where they would connect, and the A character introduces those. So the controllers, the X controllers would code up this data and then run it through ACES, which would produce a table overlay that's in your build. So that's how you get all that data from your charts and airspace structure into the system. So that's just a very small bit of AMBER 3.4. I mean, AMBER 3.4 ran all the way up to Wallasey in the Wirral, so you can see there's quite a lot of data to pass through ACES. Now, some words about the online operating system. Now, that's a list of the subsystems that's in there. Some of them are fairly self-explanatory. I haven't really got time to talk very much about it today, but just make some general comments. The operating systems available for commercial 360s weren't really suitable for this real-time application. Just couldn't cope with peaks in traffic and the variety really of real-time processing. So IBM wrote a completely new one, and it was called Monitor. Now, an important concept in 360s was that there were two states. There was a problem state, and this is where application programs would run. They'd run in problem state. There was a supervisor state where you could perform privileged instructions, and things like start.io, for example, were privileged. So these would be under monitor control. So if an application program required some sort of start.io, for example, or to use some resource that the monitor controlled, it would obey a supervisor call, which would generate an interrupt. The interrupt would allow the monitor to have control. In the meantime, the monitor might actually do some other things that the application program wouldn't know about, and then when priority allowed, it would allow the original application program to run again. Now, in a real-time environment with lots of shared data, and in fact multi-processors that want to share the data, there was a very elaborate system of locks. So if an application program wanted to write to a particular table, it would have to, that might be used by somebody else, it would have to lock it. So it would call the operating system, which would check that the lock was valid for the start, because there was a hierarchy of locks to try and prevent visual suspension of application programs. Now, memory being in short supply in those days, The monitor controlled the releasing of pull blocks to application programs. So an application program could, if it wanted to temporarily hold some input data, an input message, while it is processing it, it would release a pull block from the monitor. Now the unused pull blocks were all chained together, and the monitor administered these. And when the pull block was returned, monitor would check that the last two characters contained the characters good block. Because one of the favourite faults of application programmers was to override the end of the block they'd leased and thus destroy the chaining, which obviously was disastrous. Okay. Communication between programs was handled by quite an elaborate system of queuing. Now, the length of the queues could actually be controlled by adaptation, so you could do quite a lot of tuning of the system if you found that there were certain bottlenecks in certain places. Again, it shows how far-sighted the Americans were in using the adaptation. There were substantial online recording capabilities. You could actually code in to your program a call to the operating system to call for the recording of almost anything in the system. This would then be put onto disk, and it would then be read off onto tape, and it could be looked at later, and it was very comprehensive. And having used it myself, I would say it's probably the best I've ever seen. Now, there was quite an elaborate system of attempting to restart NAS if the monitor had detected a catastrophic error. And this was called a start over. So, for example, if the free chain pointers had been corrupted, the monitor would then declare an abort, and it would, first of all, it would dump the whole content of memory onto tape for study later, and then it would bring back from disk recovery recording data sets. It would then process those previously recorded recovery recording data sets into a set of application data from which the system could start afresh. Hopefully that would work, but in fact there were 4 sets of recovery recording going back 15 seconds at a time on disk, so chances were you might get away with it and be able to restart the system automatically in a matter of about 5 or 6 seconds from the first recovery recording data set. So you normally then just try and keep the system running until maybe some quiet hours at night when you might take some other remedial action. The application subsystems divided into basically 2 parts, as John mentioned: the flight data processing, which looks after printing strips at timely intervals. There was also a thing called the bulk file, which basically was a schedule, a timetable of flights. So it'd be basically a winter and summer timetable. And when a flight was due, the system would automatically say, okay, we have a flight due to depart in, it was generally about 40 minutes, and so to start printing strips, bring the flight data down into memory, and basically prepare the system for when the aircraft took off. If changes were required to the schedule, this was possible online by the supervisory staff. Now, radar data processing. John has mentioned that there was a link, in fact, between the FDP and the RDP. The radar data processing would track from radar plot input. It would develop a track from repeated plots of an aircraft, and it would then attempt to associate the track with a flight plan. So if all the various parameters are correct, it would say, okay, this track represents this flight plan. It could then take all the details from the flight plan and associate them with that track. It also meant that if new time estimates were produced from the radar, i.e. a real-time picture, then time estimates could be fed in to the flight data processing system as well. So if a flight was more than, I think it was about a minute late, you might decide to print a time update, a small strip which was a time update of the sector to keep the controllers up to date. I want to say a few words now about secondary surveillance radar. Is the term secondary surveillance radar familiar to many people in the audience? But there are people who don't know what it is, presumably.
Yes.
Right. The introduction of secondary surveillance radar in the 1970s made the identification of a track on the screen much easier. Radar, which originally was merely reflected energy from the airframe and produced a splodge on the screen, couldn't really be used for identifying an aircraft. And quite often controllers would radio to the aircraft to make a maneuver so that they could then say, okay, that must be BAW123 because I've just seen you turn left, which is what I asked you to do. So the secondary radar overcame this problem by interrogating a box on the aircraft, which would return to the ground a 4-digit octal code. One of the functions of NAS was to automatically allocate a code shortly before the flight was due to take off. The controller would then get this on his strip. The controller would radio the pilot would set it up on his transponder, and then the code would be returned, so we have that closed loop of identification, and so that the octal code could then be translated into the call sign of the aircraft. And the sort of thing that a controller would see on his plan view display would be a smooth track position built up over a period of time from radar plots. The leader line to connect the data, the alphanumeric track data block data to the actual present position. So here we've got which 123, flight level 370, as reported by secondary radar, and quite possibly a destination label, which is Heathrow in that case. The fact that secondary radar returned the flight level from the aircraft was also very valuable, because otherwise it would have to be passed from the pilot to the controller by radio, so it saved a lot of radio traffic. So there were also these history marks, which is kind of a trail showing where the track had been. Now, these are now generated by the 9020, and it's kind of an analogue of when people used to look at analog radar screens, where the history would, in fact, have been just where the old paint of the radar pot was fading away, so it would just fade and fade and fade. Whereas here, they're constantly displayed at half brightness. That shows 3 history marks. I think it could go up to 6. Now, John mentioned that the PRDS was produced by Plessy, and it was an exact implementation according to the same interface spec as the display channel in the United States. So here you can see a rough schematic of what the 9020 did and what the PRDS did. So the PRDS basically is really just a display processing subsystem. And here's a schematic of it. So the 9020, through channel-to-channel adapters I mentioned earlier on, speaking to the DEC equivalent, which were DX11Bs, into a common equipment group, as it was called, took the track data block data from the triplex, then broadcast it to so-called display equipment group, of which there could be 120, and each processor in here would drive one of the displays in the ops room. These equipments, I think, were 1134s. The common equipment group were 1150s, and as John mentioned, there was a bypass. So when the 9020 was not being used, which quite often in the early days was turned off at night, then radar pictures were still available through the bypass group. And the bypass group comprised 8 1134s. So the bypass group, interestingly, had to do quite a lot more than the common equipment group, because it had to do stereographic projection of all the various radar data into a common plane to display on the displays. Right. Oh yes. There's a system on here I haven't mentioned so far. Now this is a code call sign conversion system. Now I mentioned that one of NASA's jobs was to allocate the secondary radar optical codes, but of course if we turn the triplex off at night, who allocated the codes? So there was a separate system for providing optical code allocation when the 9020 and the triplex weren't there. I think we're getting towards the end. And I'm afraid to say that that is West Drayton in December 2010. You're probably wondering what happened to all the equipment that was there. Well, there was a new system down on the south coast which became operational in 2001 that did part of what was done at West Drayton, but then in various stages, various bits of kit moved down until the whole of the West Drayton site closed in very early 2008, and then as you can see the buildings were demolished later. So that's all I want to say for the moment, I think, about the 9020 and West Drayton. So it's over to Ben, who will tell you something about a remarkable survivor from West Drayton.
Thank you, Neville. As Neville just said, my name is Ben Farrell and I am a volunteer with the National Museum of Computing, and we were lucky enough to save some of the equipment that came out of that building that you saw being demolished in 2010. I'm going to talk a little bit about that and its new life at the National Museum of Computing. That's briefly what I want to cover, what IRIS is, the Independent Radar Investigation System, what PRDS is, which Neville's talked about a little bit, what they mean to each other, and then a little bit about what they did at Battersea and also how we are getting on with the restoration at Tinlock. A little bit about West Drayton as a site to start off with. We keep referring to it as LATC. That stood for, at some point, London Area and Terminal Control Centre. They used to change the acronym regularly to reflect what actually was going on at the place. As we can see there, it was the National Air Traffic Services facility until January 2008, when eventually the last military system moved from West Drayton to Swanwick. And a little factor at the bottom there, during West Drayton's lifetime, it handled 48,206,332 aircraft movements. And they're very proud to tell me that they did all of that without a single accident that was attributable to air traffic control. It's quite a feat. John and Neville mentioned this, and West Drayton became a military establishment in 1919. It was used for various things. At one point, I think it was a naval shore station, then the RAF, etc., until it was designated to become the Air Traffic Control Centre in August 1962. Neville mentioned that it started off life as the Southern Air Traffic Control Centre when we had Northern and Southern, before they were combined in 1965 to form LATC. and then the military division, i.e. the RAF of LATSE, was formed in April 1970. So what is IRIS, this thing we keep talking about? It is the Independent Radar Investigation System, and it is an isolated, i.e. standalone, radar data processing system that was built to investigate air accidents, if any should occur. And what it allowed was recorded radar and voice data to be replayed on this standalone system so that the Air Accident Investigation Branch and whoever else could look into what was going on when the accident happened and try and find the cause. IRIS, incidentally, is a small standalone installation of the Process Radar and Display Subsystem, PRDS, the thing that was contracted out to Plessey in John and Neville's talks. And there is IRIS running at the National Museum of Computing, and we'll return to those pictures in a bit. So, what is PRDS? PRDS is the thing that drives IRIS, and we'll know what it is now thanks to Neville. Process Radar and Display Subsystem, and the requirement there, in quotes, is actually extracted from the specification document that NATS contracted to Plessey, and its job was to accept radar, plot and label data, flight plan data, etc., and to display this data to the controllers. The secondary purpose, the less used purpose, again, was the bypass mode, which is at the bottom there, which was intended to provide an alternative radar display when the CCC, in this case CCT being synonymous with the 9020, was unavailable. So PRDS, as we've already seen from John's diagram, was split up into various what they call EGs, equipment groups, doing different jobs. And here are a few of them. We have the Redundant Bypass Equipment Group, or RBEG. Its job was to load the software onto all the other units and also look after them. It also could process one channel of radar data whilst doing all this in a bypass mode. The Bypass Equipment Group, which we saw briefly on John's talk again, was the main workhorse in bypass mode, and that processed two simultaneous radar channels. The Display Equipment Group, its job was to interact with the sector equipment, i.e. what the controller saw, and obey all their commands from the various configuration panels that they had, and also display the sector overlays and the track data on their screens. So there was one display equipment group per controller or per sector position, and they connected to the sector equipment group, which was basically the screen, the ball, the various buttons, etc. that you could use to interact with the system. Behind the scenes, we have the common equipment group. That was the interface to the 9020 in main mode, so that's what spoke to the 9020 during normal operations. And then the rest, which I won't really go into because I haven't really got time, were various maintenance and supervisory functions. Display configuration unit, interestingly, was a patch system to connect several DEGs, displays, to segs or sectors, so you could change which display driver drove any sector. Now this is how PRDS works in IRIS. So it's a minimal configuration of PRDS. On the right hand side in RAC2 we can see we've got an RKA5, which is just to load the software. The RBEG is responsible for that, the redundant group. So that takes the software from the RKA5 and then fires it using serial to the BEG and the two DEGs. We have two DEGs because we have two displays. So we have DEG 1 control seg 1 over here, DEG 2 seg 2, and they all talk with the RBEG and the BEG using what's called the line select unit, the LSU, basically a big serial concentrator, let's put it like that. So what we have on the right, the two main workforce units again are the RBEG and the BEG. They do the radar data processing and pass the results onto the DEGs for display. So you can just see, possibly on the right hand side, radar times 2 going into the BEG and radar times 1 going into the RBEG. There's IRIS again as it is now at the National Museum, so let's see how that diagram looks in real life. So we have seg 1, sector group 1, seg 2, RAC 1, which has the two DEGs and the LSU, RAC 2, which has the radar processors, the RBEG and the BEG. And then these two units on the side are not really anything to do with PRDS, but were what recorded and replayed all of the radar data that was processed at LATSE. So this is what we used to replay the data into the system. The very early system being an SE7000 tape unit, and the slightly more modern equivalent was called RARE and used exabyte DAT tapes for the same purpose. A little closer look at the racks themselves. We can see the RKA5 there, so the software gets loaded through there via the RBEG. That's now PB1184, I believe. They were updated. Sorry, Kevin?
Yes.
Yes. They were updated at various times as new DEC hardware became available, so we have 84s. The BEG, which does the bulk of the radar, the LSU, which connects everything together, and in the 2 decks, which drive the 2 separate equipment groups. Oh, still SE7000 in the background, and RARE, which is our current source of all the replay data. So the main role of PRDS, as we've already heard, main mode, it spoke to the 9020 or CCC via the Common Equipment Group to provide radar data as well as flight plan data to the sector positions. And in bypass mode, again, as we've seen, the RBEG and BEG were used to provide secondary radar service instead of the 9020. And very similar to the diagram to what Neville just showed, probably from the same manual. We can see CCC, that's the 9020. Sector groups on the right, so that green line is main mode, comes in, goes to the 9020, goes through the keg, to the DEG, to the sector positions, and if the CC is not available, turned off, etc., it goes this way. Instead of going to the 9020, it goes to the RBEG and the BEG, and then off to the DEGs, and then the sectors. So, restoring Iris. We were waiting to receive the system from West Drayton since about 2004, funnily enough, and they told us very convincingly that yes, you can have it this year. They eventually phoned us up in 2008 and said, now you can have it. So, March 2008, we spent a lot of time at West Drayton as it was slowly gearing down as operations moved to NERC, decommissioning and packaging the Iris system from its home with their engineers and trying to learn as much as we could at the time, so we could get it going again. A month later, it arrived at the National Museum of Computing, and we started putting bits where we thought they should go. It then took a fair few months to reconnect all of the equipment groups back together. And the thing that took the longest amount of time was the rack at the end, the RARE system, which is actually the source of our replay data. Took a very long time to get going again because we simply had no documentation or manuals or anything for it, because it was a custom system specifically designed for West Drayton. There were only 2 or 3 built, and that was it. But despite that, in the end, in October 2008, we got it working, and we saw the screens pop into life and some tracks start to appear. There's a couple of pictures of us removing the thing lovingly from West Drayton. That's me stood in the floor at West Drayton, and the 2 equipment racks on the left. That was the room, what they called the Independent Radar Investigation Room, a specific room for it, where we were moving the equipment from. And here is all the equipment as it arrived at the National Museum, all still wrapped in plastic and awaiting being unloaded. And we have the sector equipment groups on the left there, the racks all together on the right. On the right hand side you can see one of the visual display assemblies which actually fit into the sector groups, basically the screen being moved around by a certain CCS secretary on the right. The racks with the PRDS equipment in the bottom, the screen when we actually got it going again, and there is a VDA being loaded into one of the sector groups just there. You can see Ericsson being loaded. Yes, he does it. Right, so initial restoration, back in 2008, we had a few problems. These were the main ones. Firstly, the PDP hardware, the PDP-11s, hadn't been moved since they were installed in the radar room. And then, of course, 25-30 years later, we moved them into a van, bust them up to TMOC, and moved them out again. They didn't like that. So we needed to basically remove all of the PDP-11 boards, clean them, put them back together, and hope for the best. The next problem was all the LSU equipment, etc., was custom designed by Plessy to make the system work. So a lot of custom cables, etc., that they designed, which we had no schematics for and no manuals for from West Drayton. So we had to guess what they did and guess why certain things weren't talking to certain other things. Eventually we found some broken wires, put them back together, and voila, we had a bit closer to a working system. And as I've already mentioned, the thing that was the worst in getting going was the RARE recording and replay unit, simply because no one knew anything about it. It was surpassed some 10 years before when they started replaying and recording data just simply on PC. But we did get it going eventually. Since then we've been in kind of a maintenance phase trying to keep the thing going for public display. In the meantime, we've had a similar set of problems. In the room at West Drayton, the system was constantly air conditioned. In fact, they ran air conditioning through the suspended floor. We have no such luxury at the National Museum, unfortunately. So on hot days, the PDPs say, not really liking that, I'm not going to work. Again, the rare unit is still prone to problems simply because we don't know enough about it. In fact, the exabyte drives which play the DAT tapes back are extraordinarily obsolete now and very hard to get hold of and have a tendency to fail easily. Also, the DIU, standing for Data Interface Unit, the thing that connects to PRDS, there are 2 of those in rare, and one of those has also failed, so we're running on our secondary at the moment and trying to restore primary. The Ericsson display units, which you saw being wheeled about earlier on, we have 4 of those, only 4 because they are enormous and weigh a lot. We can only take 4 at the time when much trading was being decommissioned, and unfortunately the power supplies on all 4 of those have now failed. So we've used up all our lives and are now having to remove the power supplies from the Ericssons directly and mend them. Luckily, about 2 days before they were all binned, we managed to take a set of the Ericsson maintenance manuals from West Drayton just in time, so we do actually know how to fix the power supplies. And in the meantime, the IRIS restoration team at the museum is also trying to preserve the software and the radar data. So the software is what's called their RBEG Ops, RBEG Operations, is what's in the archive file, and that's been preserved now, Kevin? We have copied it off.
Copy both the operating system and I think part of the 2 channels of the recording.
Yes. There was 2 separate efforts, one to preserve the data that was on the RBEG Operations disk, and secondly to build a synchronous serial interface to record the data being played back from rare, the actual radar data for preservation. That's also been done. And now we have just a couple of very short silent films of IRIS shortly after it was got going again at the museum. So there you can see the track data moving around, just about. You can see the data blocks that Neville was talking about with flight level and what should be call sign at the top, but of course we haven't got the 9020 plugged in, nor do we have the code call sign equipment plugged in. So all the best we get is the 4-digit transponder code. There you can see the touchscreen on the bottom right, which is for selecting map overlays, waypoints, etc. And the one above, the rotary knobs, is for selecting range, the history, the length of the history leader, etc. And things like that. And you've got the rolling ball. You can't see the one on the left there, but the one on the right there for selecting the track that you want to interrogate. So that's that. A slightly more detailed one of the whole system now, going from left to right. So you've got sector group 1, again with the tracks moving around. Sector group 2. The grey unit at the top is there, it's the LSU, the line selection unit, with 2 cards in because we have 2 displays and 2 sectors. Data 1, Data 2, 1134s both running. The solid state archive file at the top, 2 PDP 1184s for radar processing. The SU7000, which is the original playback system, and the rare system running just there. Oh, you can see Peter in the reflection. He's the other guy that helps me restore the system. So that's the rare system and one of the rare occasions that it actually works. So there we go. So yes, at the end of 2008, eventually we got it going. So there's a proud Peter and myself stood in front of it just after the first switch on. We actually got track data back out of it, and then a shiny promotional photograph on the right that our photographer took at the museum. Again with another CTS secretary in it on the left. And that's it. A little bit about the IRIS system. So, we might be taking some questions now.
Thank you, Ben. I hope that Kevin wasn't controlling the aircraft yesterday when I flew into Heathrow. I did wonder. Questions?
On the IRIS system,
There will be a second of those we can't hear. Thank you.
on the IRIS system, were the 2 displays just PPIs, or was one of those C-based systems? So that you can see the flight in section. So I saw one display at West Drayton a long time ago, and it was an analysis system, but it showed the plan as you have on displays there. It also showed the mode C height level at the same time, in section through, so you can see the flight path. You can see an aircraft descend and climb, which you don't see on PPI. Was that incorporated?
That was totally experimental.
Yeah. Right, thank you.
RS certainly doesn't do any transition.
No, it was very good actually.
You feel like writing some code.
Just a comment, Ted from it. As a trainee pilot, I visited West Drayton when it was very early in its early days, and also visited the Heathrow Tower on the same day. An interesting reflection on the technology of the day, that air traffic controllers would pass their strips from one desk to the next, but there was a problem passing the strips from there to Heathrow, which is 2 miles to the south. The solution to this was very straightforward. They had a television camera looking at the right-hand end of the desk and the screen of the tower at Heathrow. I just thought that was just an interesting reflection on how things were done.
Can I borrow the mic?
That's what it operates.
Following on from that, Minicap replaced the CCTV system and the SAT to Heathrow because we couldn't afford the broadband link for television from West Drayton to Heathrow. So we had to put a computer in, which was Minicap, and that then replaced the link and the CCTV system. There was a separate CCTV system in West Drayton, provided by George and myself. Cheers.
Just as a stranger here, really, I was an end user of 9020 and Minicap. I started at London Air Traffic Control Centre in the mid-60s, and I retired in the mid-90s. So I saw the lot. And what hasn't shown here, and quite interestingly, we actually worked with the flat tops. The actual radar was flat. Now, I don't know if any of you know why the radar was flat. It was flat to accommodate a thing called a shrimp boat. A shrimp boat was a piece of plastic which looked rather like a thing you put in your garden for a plant. And the idea was, before code call sign conversion, which was our saviour, you were supposed to identify the aircraft on the 64 code, just get a second blip up on the ident, write in Chronograph the call sign of the aircraft, and then move it around the flat top as it moved. Now, we never used it because anyone with a cold would blow the whole lot off the top. But that was, I haven't seen the flat tops here, I've seen it in the Science Museum here, but that was the original, I suppose, code call sign conversion that we had at West Drayton.
First of all, thanks for a fascinating presentation. My question is addressed to all three of you. As travellers, our obvious interest was in the statistics that you quoted at the beginning of the mean time between failures. The total number of journeys, which was 48 million. Very impressive figures. In reality, what was it like at the front end? How reliable was it?
Can you have the microphone, please?
As I understand it, the radar system was extremely reliable. Hardly ever, if at all, ever went down. I don't know whether anyone else can comment on it.
Somebody cabled it during a power outage and took 3/4 of an offshore out because they managed to get it so that the radar displays were on a different feed to the computers that drove them, and they switched off half the supplies. But that was human error rather than physical failure. But that was the only time that I'm aware of where there was a total loss of radar.
As far as the flight plan is concerned, as Neville said, it was often taken offline. And what happened was you dumped out, and they call it flushing, all the strips for the next couple of hours, so the controllers had the strips, and then you used bypass. So it wasn't quite so critical on flight planning, but the radar system, apart from that one outage,
I think there were.
I think hardly ever went down.
It
Quite
tended to
incredible.
be human error concerned with power supplies that took the radar system out. I can't think of anything, any other thing like that. Mr. Johnson's thing wasn't actually reflected in
John mentioned the cost of the hardware for the 9020. He didn't say anything about the system costs for adaptation.
Well, I'm not an accountant. This would presumably be internal cost to CAA because adaptation was done by the ex-controllers who are probably on the payroll anyway. It probably cost them nothing.
That's how government should account. And probably don't now.
Hi, I'm Melville Davis. I went one time at Marconi's, worked on the Myriads that's been mentioned, and particularly with the triple prong, as we call them, configuration. And as John mentioned, if one of them didn't agree with the other two, it was voted out and off. Bringing it back on again was another matter. Now, it was also mentioned then that the 9020 had the triplex arrangement, but we didn't hear anything about how that was used. Was it simply a matter of getting sufficient capacity, or was there some sort of error checking involved?
Thank you, Mel. What you didn't mention, of course, is that you were instrumental in the studies for whether the Myriad memory could be big enough or not. It was the triplex with 3 CEs, but one was always kept as a redundant element which could be switched in at any time. So what would happen is the operational system would run in 2 machines. It would do independent things, and there was a special instruction called test and set, which enabled the 2 machines, well, there were other instructions as well, but test and set was the main one, which enabled the machines to synchronize what they were doing, because quite often they would be accessing, common data areas in the SEs. So the answer to your question is the 2 operation systems worked independently, and the third one could be switched in if there was a start over. Does that answer the question?
Yes.
More or less.
Not quite as sophisticated as the Myriad.
I'm afraid not.
Albeit that it was limited in the application.
Well, I think it's interesting from a computer science point of view that there are just 2 different philosophies. Myriad had one philosophy, and 9020 had a completely different philosophy. With the task was spread over the process, rather than the task being run in each process concurrently.
The first speaker brandished the full-scale requirements.
They're having a little conference here about how they work.
I was going to show the flat screen.
Yeah, the flat screen.
Bring that up.
Yeah, that's the one.
So here you should be able to see the flat screen. Right, so you can see the flat screens here. Here's one here, for example. Yep,
Is that familiar?
does that room look familiar to you, sir?
Yeah, it's pretty familiar.
So perhaps I want to say a word or two. Anybody interested in what's going on here? So these are the supervisors here. Basically, they try and sort out any problems. They do have update input-output devices. You can see suites of equipment here which control 1 or maybe 2 sectors. In quiet times, sectors could be collapsed. So at night, for example, I mean, it was called bandboxing. Did you use that term? And you know, you could send some of the controllers for a cup of tea or something if the traffic was light. But you can actually see there are vertical displays as well. So there was a mixture eventually of horizontal and vertical.
They were information boards, actually the orange ones.
Yeah, there's, these were CCTV.
Subsidiary radar.
And I think these were CCTV screens, weren't they?
They were flight plans and departures from Heathrow, that sort of thing.
Yeah. And in the middle, there was a lot of reception of flight plan information from airlines and so on. So this was pretty much, I think, right here, John, it was called a flight plan reception area. Is that right?
I think that was a separate room.
So, you know, an airline, if they had something that wasn't on the schedule, they would ring up, and then an operator here would put a flight plan into the system.
Yes, deviating a little bit, the first speaker waived the full SCAP Ministry of Aviation requirement at one point. I guess that was, what, 1968?
1965.
65, okay. My question, quite simply, is that I was working at the Farnborough end of the of air traffic control, trying to develop models of air traffic, the London terminal twin runway operation, and also anticipating the impact of Concorde on the North Atlantic stuff. And we did have some work on the Apollo system at Prestwick to do with that. I left there in 1964 and often wondered what the impact of all that work was. Did that, does anyone here know, did that feed into the development of that requirement?
I can't answer that.
Hidden in the mist of time.
Mr. Walter, they really does that question.
Perhaps could add the concept of independent runway usage is another one of these problems that's been going, another one that's been going for decades, you know.
Yeah.
I think they're still talking about it.
Yeah.
They haven't done it yet.
Unresolved.
Yep.
One of the immediate problems was the way in which the ATC switched runways at weekends to give the Queen a rest. It required a complete new set each time they switched of departure and arrival routes. Standard routes were changed, all the data was changed, and the routings were changed every time they changed the runways.
Like back to control.
One of the interesting things that John and Neville didn't mention was that there was one problem that the UK had that the Americans didn't experience, and that was the meridian. All of their latitudes were west. Sorry, all their longitudes were west. We had some that weren't, and that we did have. I think that when they did the original plot of the UK airspace, we used to take the output from the adaptation up to Derby County Council, who had a plotter. We found that everything was turned over at the meridian, so that required a little bit of rethought. And to go back to the other system, to the Myriad system, no more than 30 seconds of failures every 5 years. That was obviously trying to mitigate against hardware failures, and obviously, as John said, hardware failures weren't the problem. During the time that I worked on that system, I can only recall one hardware problem that was detected by the cross-checking system, and that was one of the processors got the wrong remainder when it divided by 3, which mattered because we were packing 3 characters to the word and we took the wrong one out.
I was going to give Ben a chance to sort of show off and talk about how whether restoring these machines has actually any practical benefit in the real world. In terms of jobs.
In terms of jobs, okay, I see where this is going.
Here's my
And this is just directed at the fact that I've just got a job with National Air Traffic Services. At least partly, possibly mostly on the fact of what I knew from West Drayton, I guess. I suppose the short answer to the question is yes, therefore. The people at NATS certainly seem to think that it's useful in knowing how they got to where they are now in order to understand how to carry on going as they continue to try and tech refresh and replace the systems that they currently use at Sonic. The other thing being that they're running out of people that remember or know anything about things like the 9020 or PRDS as those, as people leave and move on. So the current set of people that are know all about these shiny new things, but not why they're there and not why some of the systems that we used to use are the way they are now. So preserving things like Iris should hopefully provide the backstory to explain why the modern picture is the way it is.
I'm glad to that the importance of it is to show us, the travelling public, what a fantastic job they must have done, and how they did it. I'm glad I safely landed yesterday from San Francisco and heard this talk afterwards, but and when I saw Kelly doing the air traffic control, I wondered. Have we any more questions? Yes, Alan. Wait for the microphone, please.
Just really a comment and perhaps a follow-up question, but I'm more on computer history aspects to do with the Apollo project and one of the other speakers from my question. The Apollo project originated from an investigation in the late 50s for an automated flight information storage system called AFIS. The man Harry Johnson was involved, and that was fed out to Ferranti by the ministry. It was to drive displays designed by RRE, and it was to provide up-to-the-minute flight information on traffic conditions using displays designed by RRE and to print the flight progress slips. A machine was produced using the original intention, the original Ferranti response was to provide a Pegasus, Perseus-derived valve machine. That was obviously on the way out, and they adapted the proposal to be a transistorized machine using the Griblon circuitry that was used in the Argus computers. We've got the Ferranti brochure here that describes the machine as a machine that was aimed at the real-time operations market, and it obviously set out to capture a wider market for real-time applications. However, in fact, only one machine was produced, and it was installed in early 61 to control the Oceanic Area Control Center, which as John's mentioned. But what's surprising is that ran until 82. Anyway, somebody else can comment on that. But the other sort of computer history aspect is that then led to a whole stream of developments by the Digital Systems Division of Ferranti. The Hermes computer systems that were shown came out of that, but that was split off from the commercial computers and led to a whole series of work done on basically radar tracking systems for the Royal Navy, for fire and ship fire control systems. So that's a bit of the history. And the question really was, what was Apollo doing until 1982? It must be doing something useful.
my recollection is that there was a project to replace the Apollo system was launched with operational requirement number 1 of 1968. Because of various recessions, the project was parked and started again and parked and started again. And it's, I think it got underway, it was about 78 was that the contract was let for a replacement. And that project actually only delivered in 88. So I'm not quite sure what they did between 82 and 88 if you think the Apollo was withdrawn. And the successor system, by the way, that I'm afraid it took, which was based on PDP 1170s, 20 years in fruition. It was actually withdrawn. I'm afraid it didn't quite last 20 years in service. It was actually withdrawn 19 and a half years after its introduction into service. Computer software for air traffic control tends to have an extremely long lag. The current prediction for the 9020, although it's been rehosted a couple of times, a lot of the core software is still in operational use and has a predictive life of a further 6 or 7 years.
Just wanted to ask, what sort of, you talked about the long life of the software, and what sort of upgrades and process was needed to keep it going and till the successors arrived, and presumably from what you're saying, maybe still is keeping the necessary.
There was a constant stream of enhancements and changes from the controllers, and these were bundled up, and there would be usually 2 major releases, they'd say a major and a minor release of new software, typically in the spring and in the autumn. In the interim, if there were serious things that needed fixing, then there were very substantial capabilities in the NAS system for putting in temporary fixes that could be overloaded onto a normal build. And actually, there were lots of little tricks you could play. If you had one of these temporary fixes and you had an abort, you could actually decide whether you wanted the fix to go back in or not, or to proceed without it if you suspected that your new temporary fix was the problem. So there were all sorts of tunes they could play.
Behind you, Kevin.
A completely facetious remark, but from the commercial point of view, working on 360s, we used to have these PTFs, which were program temporary fixes, but we always used to call them permanent temporary fixes. They never got sorted out.
I one of the Nats jokes was it never called anything interim. And the interim sector update that I think Neville mentioned was in service for 15 years.
232 radar? 232 temporary radar, went on forever.
Just a comment about these printed slips and the air traffic control as done on smaller airfields around the world. I remember quite visiting International Air Radio when they were going to supply us a console. We had gone to them to build us a custom-made console for controlling communications lines in and out of the building. But I was quite impressed at the time that really the manual aspect of positioning these slips on the board was a system of keeping track of what was coming and going into any particular sector. Thank you.
Right. I shall declare we've done. It's always a feature, I think, of CCS meetings that not only do we get a fascinating insight into an application of computing back in history, which we've had today, but they bring their mates with them and they have a discussion, and we learn even more about it in that way. So it's good to have you particularly here, those of you who are air traffic control people, because we, ordinary computer people, have learned a lot. Thank you, John. Thank you, Neville. Thank you, Ben.
This is the last